So here shows the schematics of a few categories of a particle localized DC and AC electrokinetic phenomena. So picture A shows the electrophoresis. So upon application of a DC electric field, so particles migrate toward the electrode of opposite charge. So picture B shows the dielectrophoresis. So particles are attracted to or repelled from the highest electric field intensity region due to the interaction of an induced dipole with the gradient of a DC or AC electric field. So picture C shows the induced charge electrophoresis. The ICEP, unbalanced electro-osmotic flows around the particles surface resulting from different electrical properties of each hemisphere causes the particles to move normal to the applied AC electric field direction. So picture D shows the diode rectification of an AC field converted to localize the DC electrophoresis. So diode self-propels in one direction due to AC field rectification between diode's electrodes. So here shows the schematic of the origins of the electrophoresis of a negatively charged particle in a DC electric field. So the zoomed in area on the right side of the particle reveals the electric double layer at the particle surface with the surface charge, the layer of bound counterions, the Stern layer and the diffuse layer. The variation in electrical potential with distance x away from the surface is also shown. So here are the simulations illustrating the electric energy density for a pair of polystyrene particles with 100 nanometer thick counterionic atmosphere in low frequency 1 kHz AC electric field in picture A, and in a high frequency 100 MHz AC electric field in picture B. So the bars to the right indicate the intensity of the electric energy density. So direction of the AC electric field is shown with the double-headed red arrows. The simulation demonstrates how latex particles subject to low-frequency applied AC fields experience positive dielectrophoresis due to the conductive nature of the induced electrical double layer. However, at high-frequency AC fields, the induced double layer does not have time to form, and thus the low particles are less polarizable than the media and experience negative dielectrophoresis. So here shows the schematic of the concept for efficient separations during the electrophoretic transport of a fluid and analytes in a loop-shaped channel under the simultaneous action of AC and DC fields. So this is called diol pumps, which will allow decoupling of the electro-osmotic fluid flow from the electrophoretic solute motion. So if the loop channel has diodes placed on one side, then the AC field will be rectified to drive the fluid in circular motion in the channel. So know that the AC field will not lead to a translational motion of analytes in the system. They may only oscillate. On the other hand, the DC field will not lead to any type of fluid motion due to the loop shape of the channel. So it will, however, induce electrophoretic motion of the dissolved analytes or suspended particles. Hence, in part of the loop, the upper half of the loop, the solutes will be moving left to right, driven by both the convective electro-osmotic flow and the electrophoretic migration. In the lower half of the loop, however, these two fluxes will be opposing each other. Hence, species with greater electrophoretic mobility will be able to overcome the electro-osmotic flow and move upstream from left to right. So the species with lower electrophoretic mobility will be swept by the electro-osmotic fluid flow to the left. Therefore, certain species will accumulate in the vicinity of the electrode on the right, while others will continue circulating in a loop. So this concept was experimentally proven and used to separate two types of colloidal particles. The researchers reported a high-frequency measurement technique that can be applied to biological receptors. So knowing that the sensitivity of the biosensor devices suffers from the ionic screening due to mobile ions present in the solution, they demonstrate a new high-frequency sensing platform to overcome the ionic screening effect by operating a single-watt carbon nanotube FET sensor at megahertz frequency range. Electrical detection of a monolayer streptavidin binding to biotin in 100 millimolar buffer solution was achieved at a frequency beyond 1 MHz, as observed in this figure. The specificity of their work is distinguished by the fact that they detect biomolecular dipoles at high frequency rather than the associated charges. So here shows the measurement setup with AM modulated input at the source electrode. Sensor response with varying background ionic strengths at frequency 500 kHz, the black field squares, and frequency 10 MHz, the red field circles. So the solid line is the logarithmic fit to the experimental data at frequency 500 kHz. So here shows the schematic and the real images of the electrical immunosensors for point-of-care devices in figure A and B. So the ELISA employing ALP labels is combined with ISFET platform in order to impose electrical signal with a high sensitivity. In figure C, it shows the electrical signal variation of 100 nanograms per milliliter IL5 enhanced by APL label and a Debye screening lens in different PBS concentrations. So these researchers made these novel electrical immunosensors by combining the ELISA with ALP labels and an ISFET platform. And they proposed this to overcome the Debye screening effect. They verified the system through the detection of IL5. The result was a dramatic enhancement of the detection signal and circumvention of the Debye lens issue. Their sensor platform surpassed the sensing capability of the conventional ELISA that is considered to have a limit of a detection on the order of 1 nanograms per milliliter. Here shows the schematic of the three electrokinetic phenomena used for performance improvement of the biosensing devices. So in picture A, it shows the electro-osmotic slip velocity, which is generated adjacent to the surfaces of a pair of coplanar electrodes. The bulk of the liquid is dragged to motion, and therefore two vertices are formed on top of the electrodes. So for the AC electroosmosis, when a solid surface becomes exposed to an electrolyte, electric double layers are formed due to the differences in electrochemical potentials of the two phases. The solid surface is charged, causing the double layer to be charged oppositely. The characteristic thickness of the double layer is called the Debye length, and which can be calculated using electrical permittivity, average diffusion coefficient, and the electrical conductivity of the mediums. So if an external AC electric field is applied across the bulk of a weak electrolyte, a net force will be generated on the ions within the diffuse part of the double layer, causing a motion with a velocity known as the slip velocity, which can be calculated using the potential drop across the diffuse part of the double layer, the strength of the external electric field, and the electrolyte viscosity. So the bulk of the electrolyte is dragged to flow once the slip motion is generated near the walls. This phenomenon is called electroosmosis, which is based on the formation of electric double layer. Direct current electroosmosis has the disadvantages of high electrochemical reactions and electrolysis at the electrode surfaces, as well as the formation of bubbles and the macroscale pH gradient due to the high voltage usage. To minimize these issues, AC electroosmosis has been proposed, which has the advantages of operating at low voltages and generating non-uniform electric field. So the thickness of a double layer is inversely proportional to the electrolyte conductivity, meaning that for high electrical conductivity fluids, for example, the most biological fluids, the thickness of a double layer is small, and therefore the resultant AC electroosmosis effect becomes weak. Thus, AC electroosmosis is more efficient if applied to liquids with low electric conductivities. Single electrodes as well as array of electrodes with different shapes and sizes in the milli-channels have been widely investigated in literature. In Figure B, it shows the temperature gradient resulted from Joule heating causes the formation of two vortices in the bulk of the liquid on top of the electrodes. So for the AC electrothermal effect, when the electrolytes with high electrical conductivities are exposed to an external non-uniform AC electric field, Joule heating effect becomes more significant than electroosmosis. So this effect can be characterized according to energy balance equation using thermal conductivity and the temperature. So the resultant temperature gradient in the bulk of the liquid causes a permittivity gradient and a conductivity gradient, which in turn causes a net force called electrothermal force. In the bulk of the electrolyte, the time average electrothermal force can be calculated using angular frequency and the charge relaxation time. Unlike electroosmosis, electrothermal force is a body force acting on the bulk of the liquid, and therefore is not limited to the double layer. The electrothermal effect is thus a very useful tool for biological fluid manipulation. Joule heating can be generated either by applying an external electric field across the bulk of the solution, or by using an external heat source. So it can be used for macroscale fluid pumping and mixing in a lab-on-a-chip device. So Figure C shows an object with higher polarizability than the surrounding medium in the presence of a non-uniform electric field experiences dielectric force toward the high-strength electric field. So for the dielectrophoresis, the dielectric force is generated when a non-uniform electric field is applied over a suspension of polarizable objects, such as protein particles, and the medium. Depending on the effective polarization between the objects and the medium, the objects will experience a dielectric force towards the high electric field region or low electric field region. This phenomenon is called dielectrophoresis, or DEP. If an object has a higher polarizability than its surrounding medium, the DEP force will push the object towards the high electric field region. So this is called the positive dielectrophoresis. So negative dielectrophoresis occurs when the object has a lower polarizability than the medium. Now, this causes the object to move towards the low electric field region. So the time average DEP force acting on a spherical object of the radius A in the medium can be calculated using the real and complex permittivities of the particles and the medium. And the dielectrophoresis force, DEP force, is most effective near the edge of the electrodes, where the strongest electric field gradient is present, and it rapidly decays with distance from the electrode. Also, the dielectrophoresis force is very sensitive to the object dimension. In addition, in biological solutions, the protein manipulation by dielectrophoresis is frequency dependent because the effective polarization of the proteins are determined by the protein structures and their electrical properties. Depending on the phase shift of the electrodes voltage, different modes of dielectrophoresis, such as traveling wave and electrorotation, can be generated. So figure A shows the schematic of a positive and a negative dielectrophoresis force acting on bio-macromolecules at the presence of a non-uniform electric field. So for the proteins, negative and positive dielectrophoresis have been utilized to trap the specific antigen protein ATA sensing surface located at the gap between interdigitated macroelectrodes. So the resistivity measurement of the trapped molecules at various protein concentration will show a detection improvement with negative dielectrophoresis compared to a reference condition when no dielectrophoresis was applied. Also, dramatic enhancements of detection sensitivity were achieved, and in addition, the limit of detection was improved. So in figure B, it shows the schematic of the dielectrophoresis concentrated nanomolecules. The resistance difference measured before and after binding occurrence are used for sensing calculations. So as mentioned, the dielectrophoresis can be used for the manipulation of polarizable particles, such as proteins, in the presence of a non-uniform electric field. Dielectrophoresis force is size-dependent and short-ranged, which means that it is dominant at the vicinity of the microelectrodes if applied on large particles. Dielectrophoresis has gained much attention in biosensing applications for separation and concentration enhancements of different biological species, with a size range of 100 nanometers to 10 microns. Dielectrophoresis has been widely used for the manipulation of biological particles such as viruses, DNA, and proteins. Also, dielectrophoresis has been used in the field of biosensing for applications including trapping, focusing, selective separation, transportation, and deposition at a preset location of the device. So it has been shown that the dielectrophoresis is capable of trapping and pre-concentrating the DNA and the proteins near the sensor surface to a dramatic enhancement and can decrease the limits of detection. Also, planar macroelectrodes have been used to make the dielectrophoresis gates capable of a multi-target pathogen detection by performing filtration, sorting, and trapping of the bioparticles. So finally, in Figure C, the schematic shows a schematic of a multiplex detection biosensing using an array of protein-modified elements and arrays of interdigitated macroelectrodes. So bound beads on each element can be forced to detach by applying a voltage at the corresponding electrode array and utilizing dielectrophoresis effects. So this picture shows the schematic diagram of dielectrophoresis versus electrophoresis. So in Figure A, it shows the positive dielectrophoresis and the negative dielectrophoresis effects, where the dielectric particles move towards the high electric field gradient on the left for the positive dielectrophoresis, and the dielectric particles move towards the low electric field gradient on the right side for the negative dielectrophoresis. And the Figure B shows the electrophoresis in which cations and anions move towards negative and positive electrode respectively. So many people are confused on the terms of dielectrophoresis DEP and electrophoresis EP. So the DEP technique, the dielectrophoresis technique, manipulates particles in non-uniform electric field, while in electrophoresis, the particles respond to the uniform direct current DC voltage to energize the electrode and attract the particles. So the movement of particles in dielectrophoresis is based on the difference in polarizability between the particles and the surrounding medium. If the particles move towards the electrode edge, the region of a high electric field gradient, then the response is called positive dielectrophoresis, the PDP. Well, if the particles move away of the electrode edge, then the response is called negative dielectrophoresis, the NDP. In dielectrophoresis, the particles itself carry electrical potential and respond uniquely to different frequencies. On the contrary, the particles manipulation in the electrophoresis technique is controlled by the particle size, density, molecular weight, and purity. Electrophoresis of positively charged particles, cations, is called cataphoresis, while electrophoresis of negatively charged particles, ions, is called anaphoresis. Another difference between the two techniques is that dielectrophoresis technique can create a trap of particles using electromagnetic fields, while electrophoresis cannot create stable, non-contact traps of particles. So the dielectrophoresis force is initiated by applying a non-uniform AC electrical field that manipulates the motion of particles by creating polarizability gradient between the particles and the suspending medium. Dielectrophoresis technique is exploiting the mechanical and the electrical properties of the proteins and the bonding properties of the protein's surface for the uniquely induced protein motion. So when protein particles are exposed to this non-uniform electric field, two different forces occur between the proteins and the surrounding medium, leading to a resultant force. So the motion of the protein particles can be in response to positive dielectrophoresis or negative dielectrophoresis effects, depending on the relative polarizability between the protein and the surrounding medium. So this figure shows the illustration of dielectrophoresis DEP phenomena, in which a PDEP effect occurs when the protein travels toward high electric field gradient, while the NDEP effect occurs when the protein travels towards the low electric field gradient. So both of these phenomena depends on the Cm factor. So the direction of the dielectrophoresis force is independent of the applied voltage, which means changing the voltage will not interfere with the direction of the resultant dielectrophoresis force. However, the relative polarizabilities of the proteins and the surrounding medium can be manipulated by controlling the frequency of the applied electric field. The DEP force becomes zero at a specific frequency, and the particles do not move. This specific frequency is known as the crossover frequency or zero force frequency. So this phenomenon takes place when the real part of the effective polarizabilities of the protein particles and the surrounding medium equal each other. So it was established that the conductivity controls the low frequency dielectrophoresis behavior, while the permittivity controls the high frequency behavior. So to understand the relative advantages using a DEP force, we can see that in this figure, in figure A, the charges formed on a particle when subjected to an electric field E can be represented as an induced dipole moment M with its associated lines of electric field. So the induced moments of three similar particles are shown aligned with the external field. So the electrical polarization of a particle in an electric field E, through which the particle assumes the properties of an induced dipole moment M. So the magnitude and the polarity of M depends on the polarizability per unit volume of the particle. And the direct evidence of the electrical polarization of particles in an electric field can be observed in figure B here on the right, when the induced moments of neighboring particles electrostatically attract each other to form the chains of aligned particles known as Poor chains. An example can be shown here. So the electrostatic interactions between the polarized particles can result in their moving to form the Poor chains so as to minimize their electrical potential energies. So the actions for generating the DEP force can be illustrated in these three pictures. In figure A, the electric field generated by a pin electrode decreases in intensity with increasing distance from the electrode tip. And in picture B, a particle that is more polarizable than the surrounding medium distorts the electric field as shown. The induced dipole moment is aligned with the field direction. In figure C, for a particle that is less polarizable than the surrounding medium, the induced dipole moment is aligned against the field direction. So here shows the schematic depiction of experimental devices used to study protein dielectrophoresis. In figure A, it shows the quadruple electrode geometries utilized to manipulate proteins under AC conditions. So the proteins are trapped due to positive dielectrophoresis in the top image between the electrodes where the electric field gradient is high, or negative dielectrophoresis at the low electric field gradient regions in the bottom image. So in figure B, it shows a schematic image of a nanopipette used when a negative voltage is applied to the bus electrode. Negatively charged protein is moved electrophoretically into the opposite direction of a positive dielectrophoresis. Thus, DEP force and the electrophoretic force are balanced, and the proteins are trapped at the nanopipette tip. In figure C, it shows a circular insulating post array as utilized under DC conditions. The protein is repelled from the constrictions where the electric field gradient is highest, indicating negative DEP. In figure D, insulating constrictions with sawtooth shapes realized with the application of a DC voltage. The proteins are trapped at the narrow constrictions by positive dielectrophoresis, PDP. In figure E, a nano-constriction insulating device is used under AC conditions at a frequency of 100 kHz. So the protein is trapped due to positive dielectrophoresis, PDP, in the top image. So with the application of an appropriate AC voltage as well as a DC bias, proteins are accumulated continuously due to negative dielectrophoresis, NDP, in the bottom image. In figure 5, a triangular insulating post array was used with the application of a DC voltage. The protein is focused in streamlines between the posts due to positive dielectrophoresis, PDP, in the left image. Note that the flow direction is from left to right by using a tri-block copolymer above the critical concentration. The protein is encapsulated, resulting in protein-depleted streamlines due to NDP, negative dielectrophoresis, in the right image. So in figure G, the protein DEP dielectrophoresis focusing used for label-free protein detection sensor exhibiting high sensitivity. An inhomogeneous electric field is created by planar electrodes integrated on a substrate, resulting in protein focusing in the vicinity of protein receptors. The dotted line arrows show the direction of protein transport. So in figure C, it shows a label-free protein detection sensor with very high sensitivity. So the top image, C1, schematically shows a microfluidic channel cross-section. Upon AC excitation, a biomarker for a certain antigen is concentrated in the vicinity of the nanowire surface and binds to the receptors. The bottom image, C2, shows the change in conductance over time after varying concentration of the protein antigens was delivered to the device.